the incoming current is nothing but equal to the outgoing current, right? So incoming current is nothing but I1 and I2, outgoing current is nothing but equal to I4, I3. So mathematically you are going to write I1 plus I2 minus I3 minus I4 is equal to 0, or I1 plus I2 is equal to I3 plus I4. Okay, so this is regarding the Kirchhoff current law or first law. Coming to the second one, it is Kirchhoff second law or loop rule, or we call that one as the Kirchhoff voltage law also. So the sign convention to apply this Kirchhoff voltage law we had just went through. So before that we will go through the statement and we will go to the sign conventions. Okay, so the statement of Kirchhoff's second law says that around any closed loop of a network, the algebraic sum of changes in potential must be 0. So in a closed loop, algebraic sum of the potential must be equal to 0. Okay, so the change in potential must be equal to 0, or the algebraic sum of the EMFs in any loop of a circuit is equal to the sum of the products of the current and the resistances in it. That means that algebraic sum of the EMF should be equal to sum of the products and resistance. So mathematically you are going to write summation delta V is equal to 0, or summation E is equal to summation of I into R. Okay, so that is this line I am talking here. So in order to apply the Kirchhoff's second law, as you know that we have gone through the sign convention. So when you are going to take the E as positive, when you are moving towards the increasing potential, E is positive. When you are moving towards the decreasing potential, the E is taken as the negative. Similarly, the product of current and resistance is taken to be positive when you are moving in a direction opposite to that of the direction of current, and it is taken as to be negative, the product of current and resistance is taken as negative when you are moving along the direction of current. Okay, so this is the sign convention. So making use of the sign convention, when you apply the Kirchhoff's second law to the loop A, B, E, F, A, so you can see there, since we are starting with A there. Okay, so what happens, you can see there we are moving along the direction of current. So minus I2 R2, next minus I1 R1 is equal to, or plus minus I2 R2 minus I1 R1 and plus E1. So that is the sign convention. So mathematically you are going to write that one as minus I2 R2 minus I1 R1 plus E1 is equal to 0, or I1 R1 plus I2 R2 is equal to E1. So this is the mathematical equation, right? So similarly, if you apply the Kirchhoff loop rule to the mesh or the loop BCDEB, so you are going to get the equation as minus E2 minus I3 R3 plus I2 R2 is equal to 0, or minus I3 R3 plus I2 R2 is equal to E2. So this is the equation, right? So I hope it is clear, right? So in case if you have any doubts regarding this Kirchhoff law or regarding the sign convention, please do ask and get it clarified now itself. Okay, so because it is little bit confusing for this biology students and computer science students. Okay, so in case if you have any doubts, please get it clarified now itself. Do you have any doubts? Please do reply in case if you have any doubts. Okay, fine. With this, we will move to the next important derivation. Okay, that is Wheatstone network. Okay, so this derivation is for 5 marks and it is a important derivation. Okay, from the point of examination. So this question will be, the derivation will be asked for 5 marks. Okay, see, let us see what do you mean by this Wheatstone network. Okay, so just I'll read out that first paragraph there. It is an arrangement of 4 resistances used to determine one of these resistances quickly and accurately in terms of the remaining 3 resistances. Thus, if two resistances are known, the ratio of the other two can be found. Okay, so see here, coming to the figure, in the figure you can see that you have four resistors P, Q, R, S, right? So P, Q, R, S are the four resistors. So if you ask what is the use of this Wheatstone network, okay, suppose let us say that you know the value of three resistors, you have four in the figure, assume that you know the value of three resistors, okay. So by making use of three resistor, you can find the value of the unknown resistor, okay, the one which is left out, you don't know the value, you can find out that one. That is the use of this Wheatstone network. Next, since you have four resistors, okay, the next thing I am talking, so in the next part, or another use of this Wheatstone network is nothing but, if you know the ratio of any two resistors, okay, if you know the ratio of any two resistors, you can easily find the ratio of other two resistors, okay. So that is the use of this Wheatstone network. The first one is, in case if you know the value of three resistors, it is easy to find the value of the unknown resistor, okay. That is the first use. Second is nothing but, if you know the ratio of any two resistances, you can easily calculate the ratio of other two resistances, okay. So that is the meaning of that first paragraph there. So next, second paragraph I'll read out, just go through. A Wheatstone consists of four resistances P, Q, R and S connected to form the arms of a quadrilateral ABCD. A battery of EMF E is connected between points A and C, and a sensitive galvanometer between B and D as shown in figure. If S be the resistance to be measured, the resistance R is so adjusted that there is no deflection in the galvanometer. The bridge is said to be balanced when the potential difference across the galvanometer is 0. Okay, see here, coming to the figure, first I will explain in detail. See here, the figure is in the form of quadrilateral, okay. So that quadrilateral is denoted by ABCD. ABCD is a quadrilateral, and you can see there are four resistors connected P, Q, R and S, correct. So in the between B and D you have connected the galvanometer there, okay. So that G denotes the resistance of the galvanometer. You have connected the galvanometer, and that G denotes the resistance of the galvanometer there, okay. Next, you can see from terminal A and terminal C, it has been connected to the battery, okay. So the positive terminal of the battery has been connected to A, and the negative terminal of the battery has been connected to C, okay. So I is the current flowing, okay. So now, as I said, in case if you, let us assume that you don't know the value of S resistor, okay, you don't know the value of the S resistor, let us assume, okay. In order to find the value of that S resistor, okay, so what we are going to do, just what we are going to do is, we are going to adjust the resistance value of the R. In the figure you can see there, you can adjust the value of the resistance R, so that the deflection in the galvanometer which is connected between B and D can be adjusted to 0, okay. By adjusting the value of R, you can adjust the value of the galvanometer to 0, okay. When the deflection in the galvanometer shows 0, it is said to be that the bridge is balanced, okay. The Wheatstone bridge is balanced, we say, okay. So listen here, once again I am going to repeat. You have four resistors P, Q, R and S, P, Q, R and S, okay. So assume that you don't know the value of S resistor there, okay. You don't know the value of S there. So how you are going to calculate is nothing but, you are going to adjust the value of R in such a way that the galvanometer which is connected between B and D shows the 0 deflection, okay. So once the galvanometer shows the 0 deflection, it is said to be that the bridge is said to be balanced, okay. So keep in mind, whenever the galvanometer shows 0 deflection, we say that the bridge is to be balanced. So next, see here, let us apply this KCL and KVL to this network, okay, to this Wheatstone network. By making use of this Wheatstone network, okay, we are going to find the final expression. So see here, let us apply the KCL. KCL is nothing but what? Kirchhoff current law, or Kirchhoff first law we call that one, right? So apply that. See, you can see in the figure there, B and D are the node there, okay. We call B and D are the node, okay. So coming to the node B there, okay. Just a minute, before coming to node B here, I'll just show how the current gets split up here. Let it make it little bit, okay, let me zoom it, okay. So see here, now you know that this is the current I flowing, right? So when it enters the point A, okay, when it enters the point A, once the current enters the point A, what happens? The current gets split up. So in this terminal, that is towards the current which is flowing towards the resistance P, is denoted by I1. Similarly, the current which is flowing through the resistance R is denoted by I2, okay. So the I gets split up into two, so I1 and I2. So next, coming to this node B here, you can see there again at node B the current gets split up, okay. The resistance, I mean the current which is flowing towards the resistance Q is denoted by I3, okay. Next, the current which is flowing through the galvanometer is denoted by Ig, okay. Next, coming to this node D here again, so the current flowing through the resistance S is denoted by I4, okay. So next, again here after the terminal C, the current will be nothing but equal to I itself, okay. So here once again I am going to repeat, because this is an important derivation, okay, which will be asked for 5 marks. Let's see, listen here. The I is the main current, okay. Once it enters the point A, the current gets split up into two, so one is I1 and one is I2. So the current at B again gets divided into two parts, one is I3 and one is Ig. Next, the current at D comes out to be D4, okay. So this is the explanation part. So see here, next apply Kirchhoff current law to node B here, okay. According to Kirchhoff first rule, what does it say? The incoming current is nothing but equal to outgoing current, right? The incoming current is nothing but equal to outgoing current. So which is the incoming current here? At B, it is I1. From the figure, if you observe carefully, the incoming current, the current which is approaching towards the B, is nothing but I1. And you can see the current which is leaving the node B or the junction B is nothing but I3 and Ig, okay. So the current leaving the junction B is nothing but I3 and Ig. So hence the equation can be written as, see here I am highlighting that I1 is equal to I3 plus Ig. I1 is the incoming current, I3 and Ig is nothing but the outgoing current. So hence the equation can be written as I3 is equal to I3 plus Ig, okay. So the same equation can be written in another form, that is I3 is equal to I1 minus Ig. Just the mathematics, okay. So I3 is equal to I1 minus Ig. So next, you have another node or the junction in the figure, which is that is nothing but, it is a at D. D is a junction or the node, okay. Again in the DCO, which is the incoming current there? Incoming current is nothing but equal to, can anybody say, can give the answer? Yes, Meghana, I2. Just observe carefully figure. Tell me which is the incoming current. Let me see. Just give a try. I am going to explain, don't worry. Let me know. I1 and I2. No. Sajan, wrong. How about others? Just try it. Good, Meghana. It is exactly, incoming current is nothing but I2 and Ig are the incoming current. So you can see here, this is the junction D, right, or the node D. So incoming current is what? This is the incoming current I2, which is moving towards the node, I mean node D or junction D. And you can see Ig here. Ig is also moving towards the junction D, right? So the incoming current will be nothing but I2 and Ig. That is I2 plus Ig is the incoming current. I4 is nothing but the outgoing current. You can see here it is leaving the junction. So hence in terms of mathematics, you are going to write I4 is equal to I2 plus Ig. One and the same. I4 is nothing but outgoing current. I2 plus Ig is nothing but the incoming current. So both are equal. I mean, incoming is equal to outgoing. Okay, so this is how we are going to apply the KCL to the node or the junction at B and D. Okay, so is this fine? Is this fine, students? Please do reply, because only if you are understood the KCL, it is easy to apply KVL next. You will be having little bit idea how to apply. Okay, fine, good. So see here, next take the loop or mesh first. Okay, the first mesh or loop, what we are going to take is, ABDA. Just see the figure. Okay, just see the figure. The loop or the mesh, the first one which we are going to take is ABDA, that is this one, this part. Okay, ABDA. So now to this loop or mesh you need to apply KVL, Kirchhoff's second law or Kirchhoff voltage law. Okay, apply now. See, first starting from P side we are moving. Okay, in this direction we are moving. So now I am moving along the direction of current. Okay, since I am moving along the direction of current, the product and resistance should be nothing but equal to negative. Okay, it is understood, right? The sign convention, when you are moving along the direction of current, the product of current and resistance is negative. When you are moving in a direction opposite to that of current, the product of current and resistance is taken to be as positive. Okay, now see, I am moving along the direction of current, so I1P, okay, I1P should be negative since I am moving along the direction of current. So you can see in the equation 1, minus I1P, next like this. Okay, I am moving now, I just went through from A to B, next from B to D I am moving. Okay, so B to D, so which is the current there? Ig is the current and G is the resistance of the galvanometer. So since I am moving along the direction of the current, so the product of the current through the galvanometer and the resistance of the current should be negative. So in equation 1 it is minus Ig into G, correct. So next I am moving from D to A now. D to A, you can see there I am moving in a direction opposite to that of the current, right. So hence the product of current and resistance, that is I2 and R, I2R should be positive. So see the equation 1, minus I1P minus IgG plus I2R is equal to 0, correct. We have applied the KVL to the loop or the mesh ABDA, correct, students. So now we will do one thing. Now apply the KVL. Okay, now apply the KVL to the loop BCDB. Try it. Let me see. Give the equation. Start with this here from B to C. Start with B to C and give. Let me know the equation. What you are going to get. Do one thing. Is I3Q is positive or negative? I3Q is positive or negative? Yes, Rujan, negative. Good. Josen, positive. You are getting confused. Okay. See, I3Q is negative because we are moving along the direction of current. Next, moving from C to D. Okay, you are moving from C to D. I4 and S is positive or negative? I4S. Yes, Srujan, correct. I4S is positive. Yes, Kiran, good. Yes, Rakshita, good. Okay, fine, correct. Yeah, Harshita, correct. So next, we are moving from D to B. Okay, we are moving from D to B. Now, the product of current and resistance Ig into G is positive. Yes, good, correct. So the equation for this comes out to be as minus I3Q. Okay, so just go through that, just a minute, I'll just highlight it. Okay, this one here. So applying to the mesh, I mean KVL to the mesh BCDB, the equation comes out to be as minus I3Q plus I4S plus IgG is equal to 0. Correct. So this is the equation. So now what we are going to do now is, see here, in the equation, in this equation here, okay, you have the value of I3 and I4. You have I3 and I4, right? So let us substitute the value of I3 as, see here, we have already written I3 as I1 minus Ig by making use of KCL, right? Similarly, the I4 value is nothing but I2 plus Ig, right? So now let us substitute the values. Okay, so I3 can be written as minus I3Q can be written as minus I1 minus Ig into Q plus I4 is nothing but written as I2 plus Ig into S plus Ig into G is equal to 0. That is taken as equation 2. Okay, is it fine, students? Did you understand that? Just we have substitute the value of I3 and I4 there. Okay, is it clear? Okay, fine. So just we have substitute the value of I3 and I4 there. So when you substitute the I3 and I4 value, the equation what you are going to get is, it is represented by equation 2 there. Just check out once. Okay, so see, next let us say that the current through the galvanometer is 0. Okay, so the current through the galvanometer is 0. When do you say that the current through the galvanometer is 0? Okay, when the current through the galvanometer is 0, we say that the bridge is said to be balanced. Okay, so we say that the bridge is to be balanced when the current through the galvanometer reads 0. Okay, so let us say that the current in the galvanometer reads 0. So the meaning of that is nothing but Ig is equal to 0. Ig is nothing but the current through the galvanometer, right? So if that is equal to 0, what happens to equation 1? See here, just go through the equation 1. So if Ig is equal to 0, this term here, Ig into G, if that is equal to, if Ig is equal to 0, that entire thing gets 0. So hence the left out thing in equation 1 is nothing but minus I1P plus I2R is equal to 0. Correct? So that can be written as I1P is equal to I2R, which is denoted by, represented by equation 3. Correct? If Ig is equal to 0, the equation get reduces to minus I1P plus I2R is equal to 0. That can be written as I1P is equal to I2R. That is equation 3. Correct? Correct, students? Are you following? See, any doubts, please do ask then and there itself. Okay. So next here, what happens if you apply that? If Ig is equal to 0 is applied to equation 2. So here, if you apply the Ig is equal to 0 to equation 2, the equation 2 get reduces to minus I1Q plus I2S plus, I1Q minus I1Q plus I2S is equal to 0. Correct? So here, let me make it little more simpler. Okay, clear. So here, if Ig is equal to 0, what is the left out thing here? If Ig is equal to 0, left out thing is minus I1Q, right? Done. Next, if Ig is equal to 0, this is gone. So the term is nothing but, the left out term is nothing but plus I2S. Correct? So next, this whole term will be nothing but equal to 0. Correct? So hence the equation 2 get reduces to minus I1Q plus I2S is equal to 0, or I1Q is equal to I2S. Okay, So let us represent that one as equation 4. Next what we are going to do is divide equation 3 by 4. Okay, divide equation 3 by 4. So when you divide equation 3 by 4, I1 get cancelled out, and similarly I1 in the LHS and I2 in the RHS get cancelled out. So the equation what you are going to get is nothing but P by Q is equal to R by S. Okay, P by Q is equal to R by S is the equation. Okay, so this is regarding the Wheatstone network. Okay, this is regarding the Wheatstone network. Is it fine, students? You do one thing, please go through this derivation once. Okay, I'll just give a few minutes. Okay, 2 to 3 minutes. Just go through the figure first. Figure is very important. Okay, just I am going to, I'll repeat once again. See here, if you are marking, the direction of current wrong, then the entire thing goes wrong. Okay, because since you are going to apply the Kirchhoff current law and voltage law, everything goes wrong. And similarly, you need to remember that the sign conventions are very important. Okay, the sign convention, especially what you are going to consider in the starting, that should be applied till last. The same thing should be applied. You cannot change the sign convention. Okay, once you are applied in the first step, till the last step you need to retain that itself. Okay, so please make sure that the about the sign convention and about applying the KCL and KVL correctly. Okay, just please go through once again this, just go through this derivation once, figure and mathematical steps. So in case if you have any doubts, please let me know. Just go for just go through for a few minutes. Okay, fine. Any doubts, students? So any doubts, maybe it can be in the figure, or it can be in the explanation, or it can be in the mathematical steps. Please do ask. Get it clarified, okay? Don't hesitate to ask. Okay, fine. And one more thing, see, listen here. See, I just said about the sign convention, right? So see here, in some of the textbook, when you go through the derivation, this derivation can be derived in many forms, okay? In any other alternative methods, okay? So all are correct itself. Just go through the textbook, okay? And one thing about the sign convention, when you go through the different textbooks, suppose if you go through the NCERT, or if you go through the Dinesh, or if you go through Pradeep, okay, the sign convention is, in some of the books they have taken the sign conventions different, okay? So what I have taken is, as you know that when you are moving in the increasing potential, the E is taken as positive, right? Next, when you are going in the direction in the decreasing potential, the E is taken as negative, correct? Next, the product of current and resistance is taken as negative when moving in the direction of current. Next, it is taken as opposite when we are moving in a direction opposite to that of the current. This is the sign convention what I have used, okay? In textbooks, there can be the vice versa, okay? In some of the textbook, what they have done is, when you are moving along the direction of current, the product of I and R is taken as positive. Next, when you are moving along the direction opposite to that of the direction of current, the product of I and R is taken as negative, okay? So this is how they have taken. So both are correct, okay? So just follow which is convenient to you, okay? No problem if you don't stick on to anyone, okay? So what I have said, no need of sticking on to this itself. You can try the other method also, but make sure that, but stick on to whichever it is easy to you, okay? So and make sure that once you start this derivation considering one sign convention, till the end of the derivation retain to that sign convention itself. You cannot change the sign convention once you have started, okay? So if you change, the entire thing goes wrong and completely you are going to lose 5 marks, okay? So this is regarding the Wheatstone network, right? Okay, that P by Q is equal to R by S gives the, shows the condition for balanced Wheatstone bridge, okay? P by Q is equal to R by S is nothing but it is the condition for balanced Wheatstone bridge we call. So next we have meter bridge or slide wire bridge, okay? So just I'll read out that 2 lines there. It is the simplest practical application of the Wheatstone bridge that is used to measure an unknown resistance, okay? So what is the practical application of meter bridge is nothing but, by making use of this meter bridge, we are going to measure the unknown resistance. We are going to find the value of the unknown resistance, okay? So this meter bridge you have in the practical, okay? You are going to find the value of unknown resistance, okay? You are going to do in the practicals. And similarly, this Wheatstone network, coming to this Wheatstone network, see here the Viva questions on this is very important. Whenever you get this Ohm's law, experiment of Ohm's law, resistivity, okay? So whenever you get this Ohm's law series and parallel and this resistivity of a wire, okay, the question will be based upon this Wheatstone network itself. Viva question I am talking, okay? So Viva question will be asked on this Wheatstone network. So please make sure that the whatever the related, the theory part which is related to Wheatstone and the Viva questions which is related to Wheatstone network, just go through it, okay? Okay, fine. I think we have left out with a few seconds, okay? So I'll just end up today's class, and please make a practice of writing this Wheatstone network, since it is very important. Just make a practice. Even though if you say that it is very easy, when you are deriving, the sign convention goes wrong, Okay, if the sign convention goes wrong, entire thing goes wrong. Okay, so please make a practice of this derivation. Okay, so with this thing I'll conclude today's class. Okay, thank you students.
apa beda karena